Alright, so welcome to Design at Large. So today it's my pleasure to introduce Professor Brian Granger from Cal Poly State University in San Luis Obispo, California. It's probably 4 hours north or so.
Depends on traffic.
In the middle of the night, it's 4 hours, 5 hours north. He's an associate professor of physics and data science there currently. And his research interests are in building open source tools for interactive computing, data science, and data visualization. So if you've heard of things like the Jupyter project or Jupyter Notebooks, or earlier it was known as IPython notebooks or the IPython kernel, if you've worked with data science or you're in computational sciences and worked with kind of tools for managing your workflows, you've probably heard of the work Brian is leading in the Jupyter project. And this is really exciting to have him here for two reasons. One is I think, as Jim and Adam and Sean and you were talking this morning, I think this is one of the biggest, if not the biggest, software projects that's being run primarily out of academia and being sustained for about a decade or so. I guess
2001.
2000. Well, yeah. So with IPython, it's been 20 years almost, and with the current incarnation of Jupyter, it's almost a decade.
Yeah.
So as a case study in how to run a sustainable, large, and impactful software project, primarily from academia, when the traditional route is to commercialize or be acquired by a bigger company, is really amazing. And then also, on a even bigger note to set up your talk, is I think stuff that Brian's going to talk about is really changing the way we think about doing science. Right? We think about science, we practice science, and we communicate science, which is going to be essential in in the coming years when. Hopefully, when this project gets bigger and bigger with decades, it will become antiquated that we have these PDFs that we read as papers, right? It will become reading papers as PDF documents will become just as antiquated as reading parchment that's handwritten, because in the future we'll all be using tools that are developed here. So I'm really excited for this talk. So take it away.
Thanks so much, Philip. So it's great to be here. I've had a really good time visiting different people across campus today. Thanks again, Philip, for the introduction. I want to talk to you today about Project Jupyter, and in particular, stepping back from the software a little bit. I'm still going to spend a lot of time showing you Jupyter, what it is, some of the new things we're building, but want to step back from the software a little bit and think about design for interactive computing. I think there's some interesting topics there that Jupyter is getting at. A bit about my research, development, and design work. I've been in academic world for most of my career now. Started as a faculty member back in 2003 in physics. That remains my home department and my academic training. But I've spent most of the last decade building open source tools for working with code and data. This ranges everything from a recent project of mine, Altair, in the data visualization space, which is sort of very user-focused, all the way down, or I guess up on the slide, to high-performance messaging libraries that we needed to build these interactive computing systems. And so ZeroMQ is a very nice C and C++ message passing library, and we developed a Python layer on top of that is used throughout the Jupyter ecosystem. And other things in between, some quantum computing work, and then these days I spend most of my time on IPython and Jupyter. And a quick outline of the talk. First, I want to give you an overview of Project Jupyter, and in particular, the road that we've taken from the Jupyter Notebook to the new user interface we're building called JupyterLab, which I'll be showing you today. And then I want to focus on two questions. First, one related to interactive computing in general. How do we interact with programs by writing code? And the second related to the idea of a computational narrative. How do we tell stories with code and data? So, Project Jupyter. Our goal, we're an open source project. It is a community of people who have come together. All of us are part of different institutions. Some of us are in academia, others have work in industry. We have students, postdocs, et cetera. And our goal is to build open source software, open standards, and services for interactive computing. And a particular word that we like to use in our space is also reproducible. And the meaning of reproducible computing, I think, will come up here. But roughly, you can think of if you do an interactive computation yourself, you would like to enable someone else, perhaps a colleague, a collaborator, or even your future self to reproduce that and rerun that computation. So the Jupyter Notebook came out in 2011, originally under the title of IPython. Originally, the project was focused on interactive computing in Python. In 2014, we broadened the scope to include other programming languages. IPython continues to exist as the Python-specific, you can think of plugin for the Jupyter architecture. Jupyter now, down at the bottom here, supports over 100 different programming languages. We are a nonprofit organization, part of the NumFocus Foundation, which is a 501c3 that is home to Project Jupyter and a number of other open source projects that you may have heard of, such as NumPy, Pandas, etc. Jupyter, for an academic originated open source project, is fairly large. These days, I think our total contributor count is around 500, and I can't keep track. We have over 100 GitHub repositories, so it's a very high activity, fast-moving open source project. Our flagship application is the Jupyter Notebook. I'm showing you here a screenshot of the classic Jupyter Notebook that many of you may have seen or used. And the big idea of Jupyter is interactive computing, focused on exploratory data analysis, statistical modeling, and it's all in a web browser, which addresses some of the issues around working with large data sets that are not currently on your laptop, for example. And one of the core abstractions we have is what we call the notebook document format. And so this, for historical reasons, has a .ipynb file extension. Here you can see an example notebook document. This is from the LIGO collaboration that recently won the Nobel Prize in Physics for their observation of gravitational waves. And the big picture of one of these notebook documents is that it includes live code here, visualizations, and narrative text. And it combines all these things into a single document format that you can share with other people however you may want, whether that's email, Dropbox, GitHub, Google Docs, etc. And I apologize, the scaling of the screen here is such that the resolution is a little bit poor on some of this. I think that'll go away in other slides and won't be as much of an issue. So who uses Jupyter? In 2015, we did a user experience survey of our users in collaboration with IBM, and we had 1,700 respondents. The data is on GitHub, and here's one of the things that we looked at, basically what types of roles are people in when they're using Jupyter. Data scientists, students, scientists, researchers, developers, engineers, educators. You can see the others here. Gives you sort of a cross-section of how are people using Jupyter, or who's using Jupyter, I should say. It's also a very international user community. This is the Google Analytics data for the main Jupyter.org website for September 2017. This is a good metric in the sense that the way that people find our documentation is through this domain. Even though the documentation is on a separate domain, most of the traffic coming through this site leaves immediately and goes to our documentation. And you can see it's very international. So not too surprisingly, the US here is the majority of our users. Traditionally, starting in 2001, when IPython first came out, most of our users were in the US and in Western Europe. But the user base has definitely diversified across different countries. China, India, UK, Germany, Russia, Canada, France, Japan, Brazil. South Korea is also sort of hopping in and out of the top 10 here. And this trend towards an international user base is something that has happened quite recently, actually. It used to not look like this not too long ago. We're also seeing organizational usage. Here are some of the organizations that are bold enough to admit they're using Jupyter. There are hundreds more. And a lot of this is being driven by Jupyter Hub, which is a multi-user organizational version of Project Jupyter that many of these organizations are running. And then there's also a number of other companies here that offer their own cloud-based deployments of Jupyter. Some examples of that are Google has a couple different products that include Project Jupyter, and actually they are sort of coming out with a new one that they've been working on for a while just this week called Collaboratory. Microsoft uses the Jupyter Notebooks in their big data offerings, their Spark tooling, and then also they have something called Azure Notebooks. And then IBM has the Data Science Experience, which offers Jupyter Notebooks. There's many other companies here that have Jupyter, are using Jupyter internally or even in products or services as well. Another thing that we're excited about is people sharing Jupyter Notebooks. And so here's a couple examples. GitHub now tracks trending notebooks, and their notion of trending has to do with how many people have starred a given repository over some time period. You can see these days, a lot of the trending Jupyter Notebooks on GitHub are related to machine learning. You can see TensorFlow, FastAI, a lot of machine learning AI-related content. And then we're also tracking the number of public Jupyter Notebooks on GitHub. And so here's a plot. I think we're pinging the GitHub API about once a week to gather this data. So there's a little bit of smoothing there, but there's no extrapolation going on. And so there's just over 1 million public notebooks on GitHub. And there's some really interesting work being done here at UCSD. Adam Rule here has actually downloaded most of these notebooks and is starting to look at them in different capacities. And there's really interesting questions there in terms of understanding how people are doing working with code and data using the Jupyter Notebook. We also have an amazing community. And honestly, much of our growth has been driven by the emergent behaviors and usage that are coming from the community. Just a few things to mention here. Jupyter is being used a lot now to create book-length content. There's a number of O'Reilly books. This is Jake Vanderplas's Python Data Science Handbook. Along with the actual physical print book, he has a GitHub repository that has Jupyter Notebooks for all the content in the book. And this is something that O'Reilly Media and other publishers are embracing a lot. Another example here, and actually also at UCSD, is GenePattern. GenePattern is an environment that has a customized version of the Jupyter Notebook for working with genomic data. Another example that we're proud of is that researchers are starting to release Jupyter Notebooks as companion materials associated with traditional peer review journals. Here's one particular example from Nature Genetics. Another really nice example that I'll switch over here, LIGO Open Science Center. So again, I mentioned the LIGO collaboration that won the Nobel Prize. They have this Open Science Center, and if you go here, you can click on Get Started. And I think, how do I work with this? So here is the LIGO data, and their tutorials and the materials around their peer-reviewed publications are published as Jupyter Notebooks. And if all works here, I can click on this. This is something called Binder. So Binder allows you to turn a GitHub repository with notebooks into a live running notebook server. So here, anyone in the world can click on that link, and instantly there's a Docker container underneath the hood here, have a full running Jupyter Notebook server for working with the LIGO data. And so as scientists ourselves, we're really happy to see this type of usage of Jupyter in traditional scientific computing and academic research. And so at this point, there should, let's see, index.ipynb. So I could click on this and immediately start to look at their raw data and reproduce their analyses that went into their papers. Another example is in data journalism. One example is BuzzFeed, the BuzzFeed news team. There's a number of people there doing really good data journalism. And this is an example, this little screenshot here, of an article they did, I think in 2016, about match fixing in tennis. And every time they publish a consumer-oriented news article that has data associated with it, they publish the data and associated Jupyter notebooks on GitHub for anyone to go and explore and reproduce their analysis. And then I guess the LEGO Open Science Center is another example up there. Just to be clear, Jupyter is built by an amazing community of folks. Here are a few of them. This is the Jupyter Steering Council. And you may recognize some other faces that have been through UCSD recently. And it's an absolutely fantastic team. And I want to emphasize there are many other people working full-time on the project outside of the steering council shown here. And we definitely wouldn't be where we are today without this amazing community of developers working on the project. All right, so this time what I want to do is switch gears into a live demo to begin to talk you through a bit more about how we think about interactive computing and where we're headed. And to do that, I'm going to show you JupyterLab. The traditional Jupyter Notebook, again, we released that in 2014. We've been working on JupyterLab, which is sort of a next generation user interface for Project Jupyter for the last 3 years. It's currently in an alpha release. We're hoping to have a 1.0 or a beta release and a 1.0 release in the next 6 months. And here's the list of people, the core JupyterLab team. Again, credit to all these folks. They're doing an absolutely amazing job. And I get to have fun here coming and showing you what we're all building together. So at this point, I'm going to jump over here to JupyterLab. All right, so here is JupyterLab, and the first thing I want to walk you through is a bit more about just the Jupyter Notebook itself. So on the left here, I'm running the Jupyter Notebook, in this case, on my local laptop. So the files that I'm seeing are just files on my local laptop. If I click the home button there, I'm just in the home directory on my Mac. I'd see my desktop, my music, etc. This here is a Jupyter Notebook. This is one of the notebooks from Jake Vanderplas's Python Data Science Handbook. Again, the core idea here is the Jupyter Notebook is an environment for, first of all, for writing and running code interactively. So for example, I'm actually going to create another notebook here. So here I can say A equals 10, B equals 20, print A plus B. So it's designed for writing code interactively. I can import math.tab. We've got tab completion. We've got integrated help. So there's a lot of things that you need when you're working with code interactively that Jupyter provides. But in addition to that, we offer this document format that allows you to combine live runnable code with other content that typically goes along with that. And so here you can see we've got headings, narrative text. Narrative text in the Jupyter Notebook is written in Markdown, which is a lightweight markup syntax. I don't know that this notebook has any examples now, but you can also include mathematical equations using LaTeX in your Markdown. And then another abstraction that I'll mention at other times is that the Jupyter architecture and Jupyter Notebooks allow code to have output that is not just text-based output, right? So in this other notebook I had, I did the usual and I printed something to standard out, and we can bring that back. But code can also have other rich visual representations. So here's a pandas data frame, and when I look at the head of the data frame, I actually can see it formatted, nicely formatted as a table. And this rich display system is actually extensible, so you can create new types of output, new types of visual representations of objects that include things like interactivity, data visualization, and so on. So yeah, this I think is a good example of a notebook that sort of mixes code, narrative text, rich output. And just to show you another example, this is from the Altair project. Let me comment this out. There we go. So here I can see I've got a data frame, and then I have live runnable code here that I can actually look at. And in this case, the visual representation of the Python object, so the Python object is not running in the browser here. I'll talk more about the architecture in a second, but the visual representation of it is a data visualization. Now, in this case, it's not even a PNG. This is a live, I think here we're rendering it using Vega Light's SVG renderer, but you could also render this using Canvas. You could have D3, JS-based visualizations, and all that's tied into the back end with a very general way of having visual representations of objects that are in your Python code or R code or so on. All right, so there's also other building blocks that you need for interactive computing. What are some of those other building blocks? One of those building blocks is at times you need the ability to edit text files. And actually, that contrast is bad. Let me switch over to the, there we go. So here's a Markdown file. And one thing that's important is that the abstraction of the file system that we use in Jupyter doesn't require the client to be run on the same physical system. So for example, I could be connected to a supercomputer that has all my files and have the same user experience. So here's a Markdown file, and let's say I want to render that Markdown file. I can right-click, show Markdown preview, and I can immediately start to see the rendered Markdown as you would expect. Other things that you need for interactive computing are typically you need a terminal, or often you need a terminal. There's a lot that you can do in a user interface like Jupyter, but many times you still need to drop down to the terminal. So here's a full-blown Unix terminal. You can run Emacs, VI, run all the Git commands you need. So again, a terminal is really another building block that you need when you're working as a data scientist, working with data and code interactively. And so it's important to note that all of these building blocks that I'm bringing up now, notebooks, rich output, text editors, terminals, were in the classic Jupyter Notebook that some of you have already been using. One of the big things that we've observed as we've watched users and also heard back from users is that there's a wide range of workflows around code and data like this. And at times, you need to be able to assemble these different building blocks in different ways to support different types of workflows. An example is that you often start working in a Jupyter Notebook, but over time, it starts to look more like traditional software engineering. And so you need ways of integrating between Jupyter Notebooks and other types of things that look more like software engineering. So some examples that we're doing. First of all, so in JupyterLab, we have a rich layout system, so you can lay out the different documents that you have here. So maybe I want to put the Markdown above the rendered Markdown. The other thing that we've done is to build a consistent and clean abstraction in JupyterLab that allows us to have a single model for a file and then multiple views or renderers or editors attached to that. So here, I can actually start typing, and if I stop typing for a second, the rendered Markdown notices that the underlying model had changed, and it will re-render that, right? And the thing that's important here is that we didn't sit down and say, let's add real-time Markdown rendering to JupyterLab. This same workflow works for any document type you have. So for example, if you wanted to write LaTeX here, and then in the terminal type set the LaTeX, and then open up the PDF, that works equally as well. Now in that particular case, there's a little bit of subtlety because the models that we have don't automatically synchronize with the file system. So there might have to be some sort of refresh step. But the underlying architecture is there for all the different possible file types. Another example of that is, so here's a file. This is a Vega Lite file. So Vega Lite is a declarative statistical visualization library, and it encodes a visualization like this using a JSON file. And I can also right-click and open that in an editor. And then let's drag these over here. And I can scroll down here, and maybe I want to change bar to point and see what it looks like to render this same chart with points. So again, this same architecture works for all the different file types that we provide. All right, so other building blocks. I think I'm going to stop there and go back to the talk, the slides, and talk a bit more about interactive computing. And really want to stop and think, what do we mean by interactive computing? It's something that's popular, but that we haven't always thought a lot about what we mean by that. And so the question is, how do we interact with computer programs by writing code? And I'd like to offer the following definition of an interactive computation. So an interactive computation is a persistent computer program that runs with a human in the loop, where the primary mode of interaction is through the human iteratively writing and running blocks of code and looking at the result, right? And there's two key points to this definition. Well, more than that. First is that it's a persistent computer program. We'll talk about that. The second is that there's a human in the loop, and that the last is that the primary mode of interaction is when the user is writing and running code. So my usage of the phrase, yeah?
So Brian, we often talk about graphical user interfaces as being interactive computing. In fact, I think that's even like the department name at Georgia Tech. Yeah.
Yeah. So many apologies to the entire HCI community for the overloading of the term here. And the particular usage that I have here has really come out of the scientific computing community, so computational physics, that emerged in the 80s, 90s, and so on with tools such as IDL, MATLAB, and Mathematica. And in that community, we've called this interactive computing, and in referring in particular to when we are interacting with a program by writing code. And full well, and I want to admit here that the phrase interactive computing has evolved a lot through different generations. The thing that I always get a kick about is when early versions of Fortran came out, they referred to that as interactive computing compared to punch cards. And so absolutely this term is overloaded, which is why I want to acknowledge this is the particular definition that I'm going to focus on right now, fully while acknowledging that there are many other definitions. And in particular, thinking about the broader perspective of HCI, there are many ways of interacting with computers. Writing code is probably the most inhumane, right? Yet, for many goals, scenarios, and tasks, writing code is the most effective, powerful, and desirable mode of interaction. And so the focus here is really on how do we interact with computers by writing code.
Well, I think we still use code today because for some tasks it's incredibly humane.
Yes, and that's, yeah, and absolutely. But in terms of the big picture, I guess what I would say is this: you only want to write code when absolutely that is the best way of doing something. If there's another way of doing it, you probably want to do that instead. Yeah. So what do I mean by a persistent computer program? An interactive computation, first of all, is a persistent computer program. A persistent computer program is a program with state that persists across different human interactions over time. And I'll give you a few examples here. In the Jupyter architecture, this persistent interactive program is called a kernel. This follows the usage of the word kernel that came out of Mathematica, not to be confused with the Linux kernel. And there's a large degree of flexibility in the nature of this persistent state and the execution model of the kernel. Here's a few examples. One example is Immutable Namespace. This is probably the most common. It's common in Jupyter, RStudio, MATLAB, Mathematica. The Immutable Namespace model is another possible model. Some interactive shells of functional languages begin to approach this type of thing. Another model is the reactive dataflow model that's come out of things like Lighttable, Mike Bostock, his observable HQ or D3 Express. And I think the first high-profile vision of this was from Brett Victor's Inventing in Principle talk that he gave a few years ago. Okay, yeah. So what I want to do now is go back to JupyterLab and show you some toy interactive computing environments. All right, so I have this. So let's go here to GitHub and JupyterLab demo UCSD. Oops. Mistyping. Having trouble typing today, sorry. All right, so what I want to do now is show you first the mutable namespace variant. So here's a really simple Python program that implements sort of the basic interactive shell that you could think of. The namespace is a Python dictionary. We grab input from the user from standard in, and then we use Python's exec to run the string of code that they type in that namespace. There's a little bit of error handling here, and I print the namespace as we go along. So let's do Python mutable namespace. And then I can start interacting with that program, and you can see the evolution of that interactive program, right? And so what I mean by a persistent computer program is there's some state that persists across my interactions with this program. Now, there is a user interface here. Most people wouldn't call it these days a graphical user interface, but nonetheless, there is a user interface, right? I can interact with this computer program by typing and then looking at the result, right? So this is the mutable namespace example. Now to show you the immutable namespace version. So again, we're going to use a Python dictionary to store the persistent state, but this time, each time the user types new code, I'm going to clone the previous namespace and store it in a Python list. Right? So now I have basically a sequence of immutable namespaces, and you can think of the code that the user types each time as taking you from one mutable namespace to the next. Right? And so very similar model, but now the namespace is immutable. And the thing to notice here, I'm going to type the same code. So now I'm actually showing you the evolution. So the namespace is a sequence. It starts out empty, and then as I type new code, the namespace evolves. And if I type C equals A plus B, I've got that. Right? So here's the mutable namespace, where the immutable namespace, and where this model is interesting is that you can start to think about other ways of interacting with this persistent state. For example, I now have all of these in memory. Why couldn't I just rewind to a previous state? Right? And so I'll show you a simple example that does that. I call it time travel. Oops. Right, so I've got, again, so far it looks exactly the same. Notice what I've done here in the program, though, is I've defined a time travel function that will be available in the namespace. And that time travel simply allows me to say, pick a particular spot in the list of namespaces to jump back to, right? And so let's say I've done a computation and I decide, you know what? I want to rewind time, and I want to go back to the namespace at time 2. And so I can type time, oh, I guess I don't have tab completion here, time travel 2, and now I've rewound to that previous state, right? So the point that I want to make here is that this question of the nature of the kernel's execution model and the nature of this persistent state is one of the core design considerations for interactive computing systems. right? Notice the user interface that I'm using here is exactly the same in all the cases, right? So jumping back to the slides, I do not have a live demo of the last type, namely the reactive data flow. I'm not aware of any Jupyter kernels that implement that. I know Mike Bostock came in this series and gave a very nice talk about observable HQ. Another example that I can show you shortly that has some of these ideas is the Jupyter Widgets or IPy Widgets framework. And here's a simple way of thinking about it. So A equals 10, B equals 20, C equals A plus B, print C. In a reactive data flow model, if I change A, C will automatically recompute. Right? And so you're actually able to understand the dependencies between different blocks of code in that type of context. So that's another way of modeling this persistent state. So kernels for interactive computing can implement a wide variety of models for kernel execution and this persistent state. And the design consideration here is that the design of interactive computing systems should consider the nature of persistent state and the execution model of the kernel. I don't want to turn this into a statement about which model is best. I don't think we have any idea at this point. I'm saying that we simply should be thinking about this question. However, a well-designed architecture and user interface for interactive computing should work with different types of kernels, right? And the way I summarize this here is that the kernel should really be perpendicular or orthogonal to the user interface. And I think this is something that is really foundational to everything that we've built with Jupyter. And that really is that the user interface of Jupyter should know nothing about any of the kernel details. It shouldn't even know the programming language that's being used in the kernel. Nonetheless, or it should also not know about the execution model and the persistent state model of that particular kernel. So with this definition and perspective on interactive computing, I want to go back to JupyterLab and show you a couple different user interfaces that we have for interacting with an interactive computation. So I've shown you a notebook. Another abstraction we have in JupyterLab is called a console. This is the more traditional interactive computing console that looks very similar to what I was doing here. The nice variant of this that we can now provide in JupyterLab, let me close some of these files. So back in the Markdown document. So I have my Markdown document. I can show the Markdown preview. But let's say I want to actually start to run the code in this file as well, right? I can right-click on that, create console for editor. And let's bring that over here. And now I can just put my cursor there and hit Shift-Enter, and it sends those code blocks over to the console for running. And this interaction model is very similar to what's offered in RStudio. Again, the kernel here is unchanged. And actually, I could go open up a notebook and connect that notebook to the same runtime kernel. The user interface is completely separate from the details of the kernel. All right, so an interactive computation is a persistent program that runs with a human in the loop where the primary mode of interaction is through the human writing and running blocks of code and looking at the result. The part that I want to focus on now is the primary mode of interaction part. Again, writing code is a powerful but primitive mode of interaction. And my definition here does include user interfaces that offer additional direct modes of interaction that augment the writing of code. So another design consideration for these systems is the design of interactive computing systems should consider non-coding interaction modes to improve user experience. Examples in JupyterLab that I want to walk through now are data visualization, user interface, Jupyter Widgets, and then some of the file handling that we have. All right, so first Voyager. So here's a JSON file. If I right-click on that, I can open it with Voyager. And Voyager is a data visualization tool being built in the group of Jeff Hare at the University of Washington. And the idea, it's similar to a lot of what you may have seen in a tool like Tableau. And so, for example, here I see the columns in this CSV file, and I can start to drag and drop these to different visual encodings. And actually, I'm going to show acceleration versus horsepower. And it shows the specified view here as well as related views. Right? So this is a tool for visual exploration of data. The key thing here is that we're enabling a user to do this in a context where they still might be writing code. Right? And so we're working a lot on tools that allow a user to still write code when they need to, but jump into an environment like this when they can. And so that's one example of this. Another example is the Jupyter widgets. And so here's an example. So this is a Jupyter Notebook with Python code that does some image processing. So here's a very nice cup of espresso. And I want to do some image processing on that. I want to adjust the RGB levels and apply a Gaussian filter. And so I can call the edit image function a single time for given parameters. But what I'd like to do is try out a bunch of different parameters, right? I want to, yes?
What you're trying to do is just kind of remind me a little bit of what Granger was doing. We built these JavaScript to illustrate the running of backpropagation and all these things. And I was trying to figure out, because I don't really know JavaScript that well, and I was trying to learn how to do it. But if you can actually do that, so simply, I don't have to deal with that.
Yes, absolutely. And there's definitely been, in recent years, some very impressive, interactive, data-centric illustrations in browsers. And I think, what is it? What's the name of the journal? Yes, that was started recently around these ideas. The challenge is we're trying to make these things tools that everyday data scientists would just use in the course of their work, rather than sort of custom, bespoke, interactive web applications. So here, let's say I want to try out different parameters for this edit image. And so we have a function, a Python function called interact. And interact looks at the arguments to that function. And then we have little shorthand notation saying that I want the sigma parameter, which is the width of the Gaussian smoothing, to be between 0 and 10 with steps of 0.1. And then similar for the RGB limits. And when I then touch these sliders, we actually take care of recalling that function and redisplaying the result in real time. Right? So this is another example of a user interface, an interaction mode that's more direct, that augments the writing of code. Right? Write code when you need to, but if you don't need to, there may be other nice ways of doing that. The other thing that we're building into JupyterLab, and I've shown you some of this, is the ability to declare different editors and renderers for file types of many different different file types. So for example, I've got a GeoJSON file here, and I could definitely edit that with a text editor. It would not be a very pleasant experience. What if I could just double click on it and have it rendered as GeoJSON, right? And this means I'll keep showing other things. If I don't have a great internet connection, it's actually loading the maps from the internet. It may take a second for that to show up. What you should see here is a Google Maps style slippy map with the GeoJSON overlaid on top of it. Another example is a CSV file. So here's the iris dataset CSV. You can double click on that and instantly see a table rendering of that. Now, one thing that we've found is that when you make it easy for users to look at data, they're going to want to look at data. A great example of this is from a user's perspective, they're going to come across and say, oh, well, I could double click on iris.csv. Why not big.csv? Well, it turns out that the big CSV file is a gigabyte. If you try to open this CSV file, at least on my laptop in my Microsoft Excel, it actually will not succeed. So it's a very large file. Now, part of what I want to give you a sense of here is the spinning circle here is because it's actually pulling the data from my laptop into the browser. Right? We can't hide that if a user actually wants the full CSV file. What I want to show you, though, is the resulting user experience. Right? So I can smoothly scroll through the entire data set here. And one thing that we're spending a lot of work on, again, as I mentioned, is building clean model view abstractions in JupyterLab. The data model for our grid widget here does not assume that the full data set is in memory. To convince you of that, here's another demo that uses this same grid widget. And, well, let's put it back up here. Down here at the bottom, so this example here has 1 trillion rows and 1 trillion columns and is scrolling smoothly both through rows and columns, and everything is resizable. Now, obviously, the data is being generated on the fly, but the point is here to show you that the abstraction of models and views that we have in JupyterLab is sufficient to handle situations like this. Now, from a user experience, what should happen if I double-click on a gigabyte-sized CSV file? We should do something underneath the hood, maybe convert the CSV file to an arrow file, and then give you only the chunks that you currently need to look at, right? So this type of architecture would scale to that type of usage case. So again, with JupyterLab, we're spending a lot of time trying to think about ways of augmenting the writing of code to make the users more productive. Some examples, or some non-examples of interactive computing under this particular definition. So the following fail the definition because there's no human in the loop. If I just have a Python script and I type python myscript.py and it runs from top to bottom without any human in the loop, that's not interactive computing. Also, nbconvert, which is Project Jupyter's method for running and converting notebooks to other formats like HTML. R Markdown Rendering is another example. If you render a whole R Markdown document from start to finish to HTML, that's not interactive computing because there's no human in the loop as the program runs. Now, I should mention for R Markdown, you can open one of those documents and essentially attach a kernel and send code to the kernel, and that would be interactive. Tools like Excel and Tableau, I would say, fail this definition because the primary mode of interaction is not writing code. Yes, I mean, you could say that you're writing code when you write formulas in an Excel spreadsheet, but that's a stretch and doesn't really match up with the usage case that we see where Jupyter users want to really sit down and write code. Now, again, these tools are still extremely highly useful, even though they don't meet this definition of interactive computing. My point here is that there's value in focusing our attention on tools that meet this definition of interactive computing, namely a human in the loop, where the interaction mode is primarily that of writing code. And I would go further and say we really can't address the central design questions of working with data without this focus on writing code. So the last thing I want to talk about is the idea of computational narratives. Question, yeah?
Sorry, it seems like book publishing and paper publishing don't go with the interactive computing definition, or they're more on an export?
So what we see in practice is people start with highly exploratory computing where it doesn't even look much like a document, but over time it evolves into something that starts to look more like a document, eventually something that has a narrative, which we'll talk about now, and then they might convert that. And so most of our users, I think, sort of start out doing interactive computing, but eventually end up doing things like publishing a book based on that content that itself wouldn't be interactive computing. Yeah?
Do you think the architecture would be fundamentally different if your sort of metaphor was interactive thinking? That's what lots of folks are doing when writing code. They're trying to help themselves think. And do you think the underlying support structure for that would be different, the same?
Yeah, so the question is, how does this change if we think about it in terms of interactive thinking? And I would say another way that I think of the Jupyter Notebook is it enables people to think out loud with code and data. And yes, I think what they're doing in a tool like Jupyter that involves interactive computing is thinking with code and data. I think that one of the big challenges is that interacting with a computer through writing code, we have to warp our minds into a form that the computer can understand. And there's obvious benefits to that, but there's also consequences. And so, if you're a biologist looking at genomic data, you want to be thinking about biology. You don't want to be sort of interfered by this layer of code that's disrupting that thinking. And that's where I'm not quite sure, and I think it's a core challenge is, like, it would be wonderful if the abstractions that we had in code were closer to the domain-specific questions that our users would like to be thinking about. Unfortunately, I think that's not the case, and I think therein lies the friction when it comes to thinking about this as interactive thinking. So how do we tell stories with code and data? And I just want to say, first of all, this is a huge topic, the question of narrativity in interactive computing systems. I want to start to give you some of the ideas and threads that we're pursuing. So humans are evolved to produce, consume, and process narratives or stories. Storytelling is universal among humans. All known cultures practice. Humans, regardless of culture or education, acquire the ability to create stories and tell stories somewhere around the age of 3 or 4. And if you doubt that stories are important, Netflix streamed 42.5 billion hours of video in 2015. I worked it out. It's 64,000 average human lifetimes worth of video being streamed. And storytelling likely served an adaptive function in our human prehistory. There's a very nice paper that I list down at the bottom that talks about the relationship between storytelling and evolution. And the design consideration here is that the design of interactive computing systems should consider the centrality of narratives for humans. This is a quote from a grant proposal that Fernando Perez and I wrote back in 2015. The title of the grant proposal was Project Jupyter, Computational Narratives as the Engine of Collaborative Data Science. Computers are good at consuming, producing, and processing data. Humans, on the other hand, process the world through narratives. Thus, in order for data and the computations that process and visualize the data to be useful for humans, they must be embedded into a narrative, a computational narrative that tells a story for a particular audience and context. And so a lot of our thinking around Jupyter gets back to this idea of narrative. And I think it's important for us to ask the basic question of what do we mean by a narrative? And there's many different definitions. The definition that I'm showing you here is from H. Porter Abbott's Cambridge Introduction to Narrative Theory, and it's very simple. The narrative is a representation of an event or a series of events. And Abbott acknowledges that this is a very general definition. He's casting a very large net, and many other authors add additional things like causality between the events, narrative continuity or coherence, or characters or entities that are present in the narrative. Abbott also distinguishes two aspects of narrative, namely the story, as he refers to it, which are the raw events, and the narrative discourse, which is their representation, or as he often says, the representation of those events. And so based on that, you can then ask, what are the raw events of interactive computing, and what are the design considerations of representing those events in narrative discourse? I think that the obvious events in an interactive computation are the user writing code, the kernel running code, sending it back to the user, and the user viewing results. Those are always present in interactive computation. Oftentimes, there's implicit domain-specific events related to whatever you're looking at. So maybe a trading day, if you're doing quantitative finance, collision between two black holes. So these are some of the events that show up in interactive computing. And then I'm short on time, and I want to jump ahead a little bit here and talk about this idea of narrative discourse being a representation of a story, of a sequence of events. And the point that I want to make here is that story and narrative discourse often have two different notions of time. And so here, these examples are from Abbott's book. So there's two stories or two narratives here in forward and reverse order. And the thing that's interesting about this, so it's a story of someone robbing a bank, being back in time for dinner. Our brains can read either version of these, and immediately we reorder the time, the order of the events in time, right? The underlying events are the story, as Abbott would put it, but then the narrative discourse can order those events in reverse order or in some other nonlinear order. And so that relates to interactive computing in the following way. You can think of a Jupyter Notebook as a sequence of code blocks. So these are the raw events. So A equals 10, B equals 20, and so on. And then there's the narrative discourse, the representation of those events. And in a user interface like this, it's really a spatial representation, right? We're encoding those events in space. So you can imagine a spatially ordered notebook, which might make sense for some narratives. You could imagine a spatially unordered but linear sequence of cells. Or you could even imagine other visual representations, other spatial encodings of those events. We don't know really of a better word other than a dashboard, right? You could imagine interactive visualizations in a two-dimensional grid backed by some interactive computation. It starts to look a lot like a dashboard. And the design consideration here in my mind is that we start to think about these events in interactive computing and their representation or their representation in various forms. The last thing I want to show you to finish up is, thinking more about representation as representation. It really gets to the core function of narrative, and that is stories are designed to be told and shared with other people, right? And so a lot of the work that we're doing in Jupyter these days is around sharing with people. And I want to, in a very short period of time, show you two things we're working on that. The first is this. So this is another file browser instance that implements our APIs for a file browser, but that is backed by GitHub. So here, I can type any GitHub organization. So you could type LSNBG. This is my GitHub org. And I can see all of my repositories here. I'm going to show you SymPy and the quantum notebooks. And so I can instantly start browsing Jupyter notebooks on GitHub and then loading those notebooks. Right? And so I can immediately start to run it. I have not, even in this case, downloaded the notebook to my local file system. It's all in memory. Now, there is an option to save the notebook locally, but this is one example of how we're starting to think about collaboration and sharing these computational narratives with other people. Now, this is only really read-only collaboration, right? I can just look at this notebook, I can run it. At times, though, you'd like to be able to do real-time collaboration with people. So this right here is a Google Drive plugin that we've built for JupyterLab. And this allows me to store notebooks on Google Drive and then do real-time collaboration with them. And so here, let's see, and we have chat. Let's see, hi, Ian. Are you still around? Oh, nice. Right, so Ian is a postdoc up at UC Berkeley, right? And this is pre-planned. And so we have a notebook here. Hey, can you change the initial conditions? So let's run the first cell here. So here's the initial conditions. So this notebook, oh yeah, this is the wrong, yeah, this is F equals MA. We want the heat equation here. Let's drag that up there and re-render that. And delete F equals MA. Okay, that looks better. And so we can both work collaboratively on this notebook. So you can see him there changing the initial conditions. Okay, I will run it. So we can then go ahead and run the Jupyter Notebook. Oh, shoot, I don't have the movie writers available. I don't have that installed. Can you run it? All right, so he's going to run it on the kernel on his system here. And in a second, the update should, or the output should update. And you should see, there we go. So there's a visualization of us solving the heat equation. And so, again, narratives serve a function that they allow us to tell stories with code and data. And a key part of that is being able to share those stories with other people, and in cases to even build the stories and the narratives themselves with other people involved. And with that, I think I'll stop and take questions.